Welcome everyone to this week's Graphics Programming Weekly virtual meetup. We're going to be talking about the first chapter of the Vulkan guide, so an initialization and render loop, and it's going to be a lot of reading some text, copying some code, and seeing if it runs. Let me first check. I am in the right branch. I made sure of it last night. So unlike OpenGL, which allows you, for reference, I'm mostly going to be reading the text because I tend to go off script and ramble on, and I want to keep this under an hour. So yell at me if we get to an hour from now, so I'll stop, and then we'll just pick it up next week where we left off. So unlike OpenGL, which allowed you to execute graphics commands near immediately, Vulkan has a lengthy setup process. To shorten this phase, we are going to use the VK Bootstrap library, which helps a lot with this boilerplate. FYI, I'm the author of the library. Yes, this is an interjection. I feel it is necessary because it's the library I wrote, because screw you, I get to say that. Toot my own horn. As Vulkan is a very explicit API, gives you a lot of direct control. We need to initialize a lot of things directly and not let the API do it for us. So loading extensions, selecting a GPU, choosing features, and then actually creating the context objects, the instance and device. Since there is no global state, unlike OpenGL, we actually have to pass in the device or instance object into every API function call. And additionally, on Windows, it's vulkan-1.dll, and on Linux, it's libvulkan.so. These are the libraries that you link your application to so that you can talk to the Vulkan API. Linking directly to them means you have all the functions provided for you. Additionally, you can load the DLL or .so and load the function pointers. We won't get into that because it's a bit more advanced. But one thing to note is that even though we link to the DLL, any extension function will have to be manually loaded. It's not going to be provided by this by default. So VK instance, we talked a bit about it last week. It's a context you use in which to start your Vulkan application. For it, we mainly are going to be using it to enable validation layers, as well as debugging capabilities, and enabling surface extensions. Oh yeah, Hookah Logger is the debugging stuff. Once we create it, we just leave it alone for the most part. The physical device is a VK physical device, that is a representation of a physical hardware on the GPU, on the system. It represents like a GPU. It could also represent a software rasterizer, but for the most part, they intend to represent physical hardware, not software. Usually on a gaming PC, there is going to be only one physical device corresponding to the fast dedicated GPU. But on laptops, you will find that there's often two GPUs, a integrated one that's built into the CPU for low power mode, and then a dedicated one for high power. So one thing a physical device has is it not just is a GPU, but it also is the way we query the capabilities, the features, and the extensions that are available for that device. We're not going to be using a ton, but it's important to know that you need to enable a lot of things. For more advanced usage, you'll want to have access to a lot of extensions and that kind of thing. The VK device context we make on the physical device once we're done selecting it. It's the actual driver, so to speak. It's the thing that holds all the state an application needs to talk to the driver, which then talks to the hardware. Most of our commands are going to be device level commands, so they're going to take a VK device handle as the first parameter to the function. We create a device with a given list of extensions and features that we want enabled. Don't enable features or extensions you don't need. They may or may definitely cause performance issues. The best example is robust buffer access feature. Turning it on slows your hardware down because it makes the GPU robustly access all resources, whereas before it could give junk data. Now it has to give 0, and that slows everything down. We are not going to be doing multi-GPU, but by having a separate VK device object that you have to manually create, it makes it really easy to do multi-GPU. You just create 2 VK devices, 1 for each GPU. So the swap chain is the context to the presentation engine on the computer. A VK KHR surface is the reference to the window, but the swap chain is the reference to the chain of images in which we swap to present. When we create a swap chain, we request a specific size. If we need to resize the window, we have to create a new swap chain. We can't just reuse it. There is a image format used when you create the swap chain. This image format is going to be something like R8, G8, B8, B8, A8. So that's 32-bit, RGBA 8-bit. Additionally, if you had a high DPI monitor, then it might be a different format. But we need to query it and then store it, because when we make internal formats and other internal stuff, we need to make sure it matches the one that the swap chain expects to be in. Since it's a list of images, there's more than one image in the swap chain, and we can request that there be more than 2 or 3. Generally, though, 2 or 3 is the most you need, and so we request that there be at least 2 or 3 images. FYI, we can't actually request a specific number. We can only request a minimum and a maximum. So we can say at least 2 and no more than 5, kind of. But all these things are just kind of incidental and have same defaults. The presentation mode is the interesting choice that is not a constant, easy choice. The presentation mode of the swap chain is the vsync setting. There's 4 main ones: immediate mode, FIFO or first in, first out, FIFO relaxed, and mailbox. Broadly categorizing it, immediate mode and FIFO relaxed allow for tearing. FIFO and mailbox do not. Immediate mode means that when you try to present an image, it will immediately write it into the swap chain and not wait for there to be an image available to present. Meaning it will push out 2 or 3 or 4,000 frames per second, even if it's only showing 60, because your monitor only runs at 60, but the GPU can render 4,000, so it will. FIFO, it's effectively vsync off. FIFO is the inverse of that, where it will always wait for the vsync. It will always wait for the vsync signal. So this is hard vsync and will limit your application to 60 or maybe 30 if you don't need it. FIFO relaxed is like FIFO, but it allows for tearing. So what happens is if you go above the monitor's refresh rate, say 60, it will limit it. But if you are below that, it will allow tearing to happen. So this is kind of a compromise between letting tearing happen without letting the GPU run ahead of itself. Owen asked min equals max. Yes, you can sometimes set the swap chain image count minimum and maximum to the same value. You'd have to look at the spec for clarification, but it's possible. FIFO present mode mailbox is the last one, and it's pretty interesting. It runs a bit like immediate mode, but it doesn't allow tearing to happen. So in mailbox, if you render an image and the queue is full, the swap chain image chain has been rendered to all the times it can before a monitor refresh cycle has happened, it will swap out the oldest one in the queue, but it won't allow it to be written to while it's being presented. So tearing cannot occur. Don't use immediate mode unless you want to drain battery. It's short and simple. Mailbox is interesting, but FIFO and FIFO relaxed are fine. We're probably going to be using FIFO relaxed because it's that nice compromise, but it does allow tearing. So if you don't want, and this is something you'd want to set as an option for the user of the application. So we've talked about all the various components that are the initialization aspect of the API, like pure initialization, not setting up the renderer. It's the components of the renderer. So we're gonna what? What's the question?
One quick question. Yeah, I was wondering, is there any usage differences? Like this is just a setting that you would enable. It's not like anything else that you would have to do to change that usage.
Present mode, there is usage difference because of the way the blocking nature of calls. There's a function called quPresentKHR, and with FIFO and FIFO relaxed, it will block, but in immediate mode, and I believe mailbox, it won't block. Yeah. So going forward, we're just going to start blazing through it. A lot of this is copy and pasting code. I'll try to point out things that are necessary. So we have started with the chapter 0, and I have it in a branch called Trials Progress. I was working on chapter 0 last night, going through it, but I reverted it back. I named the branch wrong. Whoops. Okay. So the first thing we got to do is go to the engine.h file and add in this, engine.c++.cpp. And we're going to be editing this file a lot. We're going to add in the Bootstrap library header. Oh, I didn't want to do it up here. So we'll be able to access the bootstrapping helpers. Additionally, we want to have a macro that allows us to check function calls. So this is a macro that we do something like, just to put it in here, vk check, vk is my function. Vulkan functions always return void or vk result. And so this will, for functions that return vk result, it will check the value if it's not 0, i.e. this is not equal to 0. Then we've detected an error and we need, because 0 is equal to vk success, the success code. And if we do, we print out a message saying, hey, we failed somehow and we abort. So this is a handy macro that I very much recommend. You always want to check the return codes, and this makes it really easy to check it. And usually you just abort anyways. So now we can actually start initializing, adding the things we're going to need into the Vulkan engine.h file. So we're just going to copy and paste the various handles. So these are handles. In Vulkan, the concept of a handle is effectively a pointer. So if you actually look at the implementation of this, if I hit F12, it should come up. This define handle macro uses it's this typedef struct object of type T star with that name. The gist is it's a pointer. Now it's not a pointer you can dereference, and you can imagine it like an opaque pointer. What it points to is not something you can understand. But it's important to know that while they're all just pointers under the hood, it's better to think of them like uint64t integers, because the lifetime semantics is completely defined by the API, not by the host language like C. So you can freely copy these handles around. Someone's comments, handles are literally pointers. In 32-bit mode, if you actually go to the definition in 32-bit mode, handles are uint64ts. They are not pointers. So it's a bit misleading to say they are literally pointers, because they're not always pointers. We also Oh, we need to add the functions we're going to have. So I'm going to add the Vulkan initialization functions here. There's going to be a whole list of them once we're done. So we now get to implement the init function with a bit more meat in it, and it's mostly going to be calling helper functions. So we're going to go from Vulkan engine init and ignore the stuff I added here. It was just to make my life a little easier. So we're going to call init function after we've created a window. And now we need to actually create the function and add stuff to it. So in this function is going to create the device, the instance, select a physical device, and I believe create a surface. So this is the code to create an instance. We create a builder object from the Bootstrap library. We call member functions on it using the builder pattern. So we want to set the application name. This is just any name you want to name your application. This is useful for drivers to see, oh, this is some big name game. This name corresponds to that big name game. So I'm going to apply my own driver optimizations internally. But because we're doing hobby stuff, I'm doing hobby stuff mostly. This is just for the fun of it. Validation layers, we definitely want to enable validation layers pretty much always. When you're doing performance measurements, be sure to turn them off, but otherwise they will catch your mistakes, and it's good to have. We're going to request version 1.1, so major version 1, minor version 1. This will allow us to use some features that's not in the base 1.0 spec, very helpful. And this last one, the default debug messenger. The debug messenger is a mechanism to allow the validation layers to return information. So it's a callback internally. Because the application doesn't do anything very specific, the Bootstrap library provides a debug messenger callback, and we're going to use it. So we're just going to, and FYI, this value thing gets the value out of it, and it will assert if it failed. So this will crash if the instance failed. So if you want to gracefully handle it, be sure to change all the uses of .value to something more interesting. And there's examples of it in the repo. Because we don't want to include the Bootstrap header in the engine.h file for compilation speed reasons, we pull all of the guts out of the object and put them in our own handles. You can store this VKB instance, or you can pull out the things, and it's just fine either way. Let me copy and paste and then answer a question that came in. So someone asked, why not use 1.2? It offers some features, but go away. It doesn't offer that many useful features for the beginning part of the tutorial, and it's not as available. It's very available, I would say, nowadays. People have been updating their driver. It came out in January of 2020, but people still haven't updated their drivers sometimes. So if you want to support a lot of people, you don't want to do a too new of a version. I just explained all these things. So now that we've created a instance, we can select a physical device and create a device from it. So we first need to make a surface. The reason we make it after we create the instance is because the surface object is tied to the instance, and we need to have that surface object to be able to select the correct physical device. Say we created a surface and it was incompatible with one GPU for whatever reason. When we select the physical device, we want to be sure we can use that surface. That is why you see the set surface function. So like before, we have physical device selector, and it uses the builder pattern. So we set the things we want. We want to set the minimum version. We want to make sure that the GPU we're using is 1.1. And otherwise, we're just going to use the defaults the Bootstrap library chooses. The Bootstrap library does prefer discrete GPUs over integrated. You can force it to use integrated if you want. It's very easy. It's just a function you call. So we're going to copy and paste this over into here. And well, we again call value to get the VKB version of it that contains the physical device handle and some other stuff. Then we put it into our own variable that we've created in the VK engine file. For creating the physical device, we just need to provide the VKB device object. It has all the information in it needed, so it makes it really easy. Usually there's not much you need to do after you've selected a physical device to create a VK device. Yeah, so for comparison, this code is 116 to 150, so it's 35 lines of code. In other tutorials, there are about 4 chapters spent on this amount of code. Because of the helper bootstrapping library, it reduces all of it down and makes it manageable, because this code is not very interesting. It's not Vulkan's interesting bits. It's the boilerplate bits, so it goes away. So someone asks, what's the distinction between a dedicated GPU and an iGPU? Well, as far as the API is concerned, there is a VK device type enumeration. If I go to VK device property, physical device property. Why can't you? Oh, I'm annoying. VK physical device properties. Device type. So the device type, this is the only real thing that distinguishes them as far as the API is concerned, whether they say it's discrete or an integrated thing. But a more direct thing is a discrete GPU is going to be a card you plug into a PCI slot. A integrated GPU is one that's going to be on a CPU. So, yeah. So now that we've got device, physical device, and instance set up, we can move on to the swap chain. For this, we're going to need to add some more variables. And we're going to just copy and paste them in. Make sure to delete those because those are not anything else helpful. We also have a new function for this that's just going to be for swap chain. So there's the changes there. And then since we're going to be pulling out there is a VKB swap chain object like the VKB instance and physical device, but we're going to be pulling out all of that stuff into our own structs. Since the swap chain is a chain of images, i.e. an array, we're going to use a std vector to store the image. In Vulkan, the VK image is like a pointer to memory, whereas a VK image view is a, can you hear the Facebook notifications? Because I can, and that's very annoying. I'm going to turn that off. There we go. Sorry about that. The VK image view is how you provide a view onto the image. It might be the whole image, but it also could be parts of it. Swap chain image views are how we reference images. So we need to create image views to view the swap chain images. Okay, good. No one else was hearing the notifications, according to chat. So I copied those in, and now we got to copy in the function. But first, we actually have to call the function. I've made the mistake before of not calling the function and wondering why it never worked. So I have the function here. I'm just going to copy it and slap it at the bottom of the file and briefly talk about it. To create a swap chain, we just provide the physical device, the device, and the surface we want. Then we select the parameters. Here we're going to use whatever the default format is, which is like the 8-bit buffer. So, and we're going to use the FIFO present mode, at least here. It's very easy to change it. You just change, this enum to something like relaxed. The builder will make sure that it's supported. Not all presentation modes are supported on all hardware. I think FIFO is the only one that's guaranteed. We also need to set the extent. I believe the Bootstrap library will get it, will try to use the current extent of the window if you don't provide one, but it's always good to provide one since we know what it should be. I think I just went over that. Yeah, we build it, we get it. Now, the nice thing is the bootstrapping library does have a way to get the images in the image views very easily. And that's what we do here. Why are there red things? I'm going to try to compile it. It fails to compile. Why did it fail to compile? Oh, right. I think this is a bug in the tutorial, but std vector needs to be included in the main header here. So that actually is a bug that I probably should have. Yep, okay, it works. And you can see we still have a white window because we haven't started drawing anything. Okay, lastly, we created a whole bunch of stuff at startup. We need to destroy at shutdown. So we'll go to the destroy cleanup function, and we're going to copy and paste all this. There is a pretty strong order that you need to follow. You can't destroy an instance before you've destroyed all child objects. You can't destroy a device before you've destroyed all child objects. So you need to do it in that order. It's pretty simple. You just delete things in the inverse order that you created them. And that's basically it. To showcase validation, because validation is very important, if I bring over the line window, we can see that this is a totally unrelated error just because I have stupid Galaxy games overlay and it's broken for some reason. I'll fix that at some point. But you can see that it prints out an error. But that's not a validation error. What we can do is we can destroy the device before we destroy the child objects, which is the swap chain and the image views, because you create the image views from the device and from the swap chain. So we need to be sure to do that. So if I do this, the application should start as normal, but when I exit, it crashes for one, and I get a whole bunch of validation errors, like in it that says object error, device has been VK image view has not been destroyed, but the device has. And then it tells you exactly where in the spec it is. So if I copy this thing, come on, there, and go to it, it will take me right to, if it will load, this links right to where in the spec the violation has occurred. So, so this is a pretty generic one, but this will help you if you don't understand why you've done it. You can read all the other things around it. So we can shut this down so we can move on to the tutorial. So now we get to the actual commands. This is getting into the interesting part. This is the basic diagram of how command buffers are used in the API. We have a command pool, which is the allocator. We allocate a command buffer. Then we can encode commands onto it, recording it. Then we finish recording it and submit it, and then it's queued. When it's finished being executed, it moves back to being able to be recorded. So it's kind of a loop here on this side. That isn't explaining what the command buffer is. So unlike OpenGL or DirectX pre-DirectX 12, all GPU commands have to be recorded in a command buffer. You then submit the commands to a queue, VK queue. I explained what the flow is above just now, so I won't repeat it. Except I will say you submit it to a queue, and the queue objects are what we're going to be trying to expand upon more in this chapter, because it's not has not been explained a lot up to now. You can record a command buffer once and submit it multiple times. It's not that common, but it's in practice, but a lot of tutorials did it initially and then everyone said, oh, we need to do that because that's what the tutorials do, and the tutorials turned out to be wrong, and I fight that fight. But in this tutorial, we're going to record the command buffer right before we use it, submit it, and then re-record it for the next frame. Question is, D3D is deferred context, kind of like a command buffer? I have no clue. I do not use DirectX 11. You have to ask in the DirectX server, Discord server. They have a lot of good people who answer questions there. A thing to note, in a lot of early tutorials, it was lauded that command buffer recording is expensive and you need to make sure to not do it a lot. But in practice, all command buffer recording is writing some data into a memory array. Like, you just say, okay, well, there's going to be a draw call, and here's the parameters, and you just write that into a buffer, a memory buffer, and that's it. D3D12's command comment says D3D12's command list is very similar to command buffer. D3D12 and Vulkan are so similar that you can write one API over them and actually get away with it pretty well. You can't say the same about OpenGL and Vulkan, nor OpenGL and DX12, but DX11 and OpenGL are pretty similar. That's a tangent, though. The nice thing about command buffer recording in Vulkan is that they're always able to be recorded in multiple threads. You have to have separate command pool and command buffers per thread. So if you want to record in 10 threads, you need 10 command pools to record 10 command buffers. But then you can do them all at the same time. And then you can all submit them at once at the very end with a single view commit. VKQ submit is not thread safe, so you have to externally synchronize it, as the text states. In other words, slap a mutex around it and make sure no two people are calling it at the same time. So VKQ, it's an execution port for GPUs. GPUs have multiple queues available commonly, and they can be used to issue work concurrently. So if you have separate submissions happening at the same time, they actually may be submitted at the exact same time and not just time shared behind the scenes. This is very useful for doing things like transfers or compute work that are in the background that don't need to operate every frame. They can happen when they need to happen, and they're not going to block the main rendering queue. In Vulkan, the concept of a queue family is an organization tool for drivers. Drivers expose a number of queue families. A queue family has properties and a queue count. So a queue might support multiple types of operation. A queue family might support multiple types of operations, say a queue family that supports graphics work, transfer work, and compute work. And then the GPU might expose another queue family, so queue family B, and whereas the first one is queue family A. The queue family B might only expose transfer operations. Each of these queue families might have multiple queues in them, so you can have 2 or 4 or however many queues there are in that queue family. We're just mainly going to use a queue that has graphics and presentation support, and we'll mostly be using only one queue because usually this is the same queue. Very, very commonly that the graphics queue supports presentation, and we'll use that, the same VKQ object for both operations. If you want a good guide on differences between queue families, the vulkan.gpu.org has a whole bunch of reports, and it has a whole bunch of information about GPUs, but the listed one I'll put into chat, and you can compare the different capabilities. So these are like the capabilities: supports present, graphics bit, compute bit, transfer bit, and you can see that they are not the same in between both. Also here there's 16 queues, but here there's only one. It's not, just make one. Don't worry about there being 16. So let me get this back over. So
what's the significance of there being 16 queues?
NVIDIA has decided that there are 16 queues that you can get access to individually, so that you could theoretically give a thread a queue. Because queues can only be accessed by one thread at a time, you could conceivably give each thread its own queue so it doesn't have to synchronize them. Except I wrote a test a couple of weeks ago that submits work to either 16 queues from 16 threads or one queue from 16 threads, and one queue from 16 threads was several times faster. It's a very lossy test. It doesn't actually do rendering work. It just sets the pipeline and the scissor over and over again. So it's not really doing real work, but it's interesting that locking a mutex takes more time than each queue getting its own thing. I have a hunch, and I have not been able to confirm it, that on NVIDIA hardware, those 16 queues are actually multiplexed internally to the driver and not to the, so instead of it being externally multiplexed with a mutex that the application controls, it's internally done for you. That's what I think. I don't have any proof or anything though, so go with that. Transfer only queues are useful. You can submit transfer work and have it run in the background. Very nice. So command pool, it allocates stuff, specifically memory for command buffers. You have to create a command pool for each queue family you want to use because it's associated with a queue family. So that's something you got to think about. Because we're re-recording command buffers every frame, we're just going to reset it. And we can reset the entire command pool, which would reset all of command buffers allocated from it for you, or you can reset them individually. You just have to turn on a flag for it. If you allocate multiple command buffers from a command pool and need to reset them all at once, resetting the command pool is probably a better bet. So now we're actually on to the start of the show, the VK command buffer. Any functions we want to execute, go through it. We always have to begin the command buffer for recording. This is the begin command buffer. Kind of like a draw list where we have to start the draw list by saying, hey, we're going to start a draw list. Now we can start, once we've begun it, we can do VK command functions. A function that writes to a command buffer always starts with VK CMD, as evidenced here. When we've done all of the calls we want to that we want to record onto the command buffer, we call end command buffer. This marks it ready for submission. So a thing to note, command buffers, when they are submitted, are considered in use. You can't touch the command buffer while it's in use. You can't begin it and start recording. You can't destroy it. You can't reset it. You have to wait until it's no longer being executed. But once that's happened, we can reset it and then start recording commands on it again. A nice chapter about the life cycle of command buffers is here, and this is probably the most informative page of text in the whole spec, I think. It's concise and tells you what's happening, and I will link it in chat, and I implore you to read it. This is good stuff. So now we actually can get into the code for that. So we want to copy the variables we need for here. That was the wrong file. We're going to need graphics queue and the family it's from. So a queue family, by the way, is an integer index. So if a GPU has 5 queue families, which is a lot, it will have 5 queue family indexes, and you use an integer index to address that. Like when you look for queue families, it's just an array of queue family properties. Properties is a struct holding some information about the queue family. And so there's nothing really special about the order other than it's the exact order the driver tells you it is, i.e. the same index each time. So we're going to add the variables. We also want to store command pool and command buffer. We also got to add our function at the bottom, init command buffer commands. We can save it. Now we got to call the function in the .cpp file at the top where we're initializing everything. So even though we've created a device, we haven't gotten the queues from it. What we'll want to do is we'll copy these 2 lines here, and we'll use, again, the bootstrapping library to get the queues from it. I believe this is the last place we use the bootstrapping library because there's just nothing else needed that's boilerplate from it. So we ask for the queue, specifically the graphics queue, which we assume supports present because it almost always does. And we just get the queue directly. We also want the queue family, which is, in all honest to goodness, probably going to be 0, but hey, you got to make sure you get the right value in case it isn't. So now that we have the queue and queue family, so this is a VKQ object, whereas this is a uint32 value, or handle, not object. So now we can create the command pool. We can just copy this function down here and paste it. To create the command, we have to create this struct here, vk command pool create info. This is the struct we fill out with the information, with the parameters we want. Vulkan, instead of having functions that take 12 parameters, puts all of that stuff into a single struct, and then you pass the struct in. So we have create command pool. We have to pass in the device context handle, and then we pass in the address of the struct, so command pool info. Null pointer here, this is the, if we look at the argument list, that's the allocation callbacks. That's a mechanism for debugging stuff that is never used in normal code because it's not that useful, and I pretty much just ignore it all the time. And then lastly, because Vulkan is a C API and the return parameter, the return value is a VK result, we have to use out parameters to get the handle out of it. So we give the address of the command pool handle, which is in the right here in the Vulkan engine class. So we give it the address of this variable, and so that the API will put the handle into here. And when we use the VK check macro to make sure it succeeds and doesn't fail. The thing that we wanted to do in the setup, or the parameters we want to pass in, is we want to pass in the queue family index. So that's saying that we're going to use the graphics queue family for this command pool. And we want to add in the create reset command buffer bit. So many structs have a flags field. This is an easy way to customize the object. And so we set the flags to a bit mask containing the flags we want. If there was another one, we would use an OR statement here and command blah, blah, blah. But since we only have one flag, we can just set the value directly. So with that, we have our command pool created. Also, C, I think ++. You always want to use this thing here or this. It's the same thing. This is this curly brace pair here initializes the struct with 0 values. That's really important because a lot of Vulkan structs contain pointers. And if the pointer has a junk value in it, that pointer points anywhere, and the driver and validation layers have no idea what that pointer points to, so they have to try to dereference it because it's not null. They don't know that it's junk. So while we explicitly null out the pnext pointer here, this is a void star pointer, FYI. While we explicitly do that, we don't have to if we have this here to re-zero out the struct first. So always do that. Many crashes are just because we have junk values in there. And I don't want to show you because I think it's not that interesting, but you remember if you start getting weird crashes to make sure all your pointers are nulled out properly. So we have a command buffer pool, and we now want to allocate a command buffer from it. Because it's like an allocator, we create the object and then we use it to allocate stuff. So I'm just going to copy it. So again, we have a struct that holds all the parameters we want. We have the command buffer allocation info struct. We null it out. We set up all the things we want. So for here, we have the command pool parameter. We pass in the command pool handle. We only want to allocate 1, so we're set the command buffer count to 1, and we set the level to primary. First thing to note, I didn't talk about above here is the S type. Because Vulkan is a C API, there are cases where the API sees a struct by void star, and it doesn't know what the type of the struct is. To allow the API, the drivers to know what the struct is, we provide an S type. This makes it clear exactly what type of struct it is. It's not strictly required for functions that take a struct by type like this one, but there are structs that need to have it because there's literally no other way for that type information to be propagated. So here we call VK structure type command pool create info, which is the same thing here. And down here we have, can you compile build solution so that the squiggle bars go away? Oh, I forgot to include IOStream. So that's why it's being annoying. Include IOStream. That happened way earlier in the tutorial and I forgot to mention it. There, all the squigglies went away. So same thing happens here. So the command pool, this is the command pool we want to allocate from for the command buffer allocation. The command buffer count should be self-explanatory. And the command buffer level. There are two levels for command buffers, primary and secondary. A primary command buffer is kind of a regular command buffer. You record it, you end it, you submit it, and you wait. A secondary command buffer cannot be submitted. It can only be called from other primary command buffers. And so a secondary command buffer allows you to organize it and do some multi-threading stuff more easily, but it's not really of any interest for this tutorial, and we're just going to be using primary at all times. So then we call allocate command buffers, and we write it into the main command buffer. So we have allocated a single command buffer after this function. In the interest of code organization, we're going to move a lot of this stuff into the initializers. Because this is pretty boilerplate. We have these structures we fill out. We got to put in the S type. It's pretty verbose, what we're doing. Instead, we're going to create a function to create a command pool and one to allocate a command buffer. I'm going to copy the definitions, paste them in here. You can see that the parameters are Q family index and the flags. But we're not actually, okay, I misread it. We're not actually creating the pool in it. All we're doing is filling out the pool create info struct. So we're going to move to the initializers and pretty much just copy and paste over. What you can see is that we're taking the parameters like Q family index and flags and putting them over here. Their comment says they're creating the create info. Yeah, that is what we're doing. And we're doing the same thing for command buffer allocate info. We're just filling in these variables that were done before. So I got to save those files. And now we can replace the code we just had. So we had all of these lines, you know, like 20 lines, 30 lines, and we can replace it with these, which I will do now. And we can look at the format of the code and see that, come on, we get a command pool create info struct from calling the function by passing in the parameters. Then we call the function as normal. And we do the same here, and we've made it a lot nicer and easier to use. So lastly, before we finish this chapter, and I think I'm going to end here because we're not even halfway through this first chapter, and there's 4 more sections to go through, and render passes and rendering loop are not something I can talk about in 5 minutes. So I think we're going to end after we clean up from here. I have to scroll back down. All we got to do is destroy the command pool. But you may ask, we allocated a command buffer. We created 2 objects. Why aren't we freeing 2 objects? Well, the command pool is an allocator. Ooh, I did not fix that. Whoops. The command pool owns all of the command buffers residing inside of it. When you destroy the command pool, it destroys all of the command buffers that were allocated from it. This makes it really easy to clean up because you don't have to destroy a bunch of command buffers. You can just destroy the pool it was allocated from. And that's why we only have to destroy 1 object. We have everything we need to start setting up the actual rendering pipeline. Let's see if it compiles. And it does, and it also runs, and we get no log because we're not drawing anything yet. But next chapter, next week, we'll definitely draw something. A closing note, we're already at a point where you could start doing compute work, like offline computation. It'd be very easy to do that. The render pass and pipeline setup is what really makes rendering difficult and rendering rasterization difficult. And we're going to be doing that, I think, next chapter. But without the rasterization pipeline, it's actually pretty easy to get work going in the compute world. You have to do a lot more manual synchronization if you're trying to do a lot of compute stuff, but for simple stuff, it's actually quite easily. Someone asked, what's my favorite Vulkan queue? Intel iGPUs, because there's only one. Those vulkan.gpuinfo.org. Just show you, actually, it'd be a good idea to go over some of the different queue organizations. Where is here's the 3 common ones. Yeah, the websites like to show me ads. It's weird. So we'll just get one from all the major things. So the queue family for the RTX 3080 Ti, there's a graphics queue, there is a transfer queue, and then there is a compute and transfer queue that also supports percent for some reason, and there's 8 of them. I don't quite know what's going on. Whereas on RX Vega, the AMD card, there's one queue that supports everything. They all support present. That's fun. There's one queue that supports compute and transfer, and then there's another queue that supports just transfer. And I ignore sparse binding because sparse binding is an advanced use case. Notice here it's 1 queue, 4 queues, and 2 queues, whereas NVIDIA there's 16 to 8, which is a lot more. There's some other things on here. Granularity, I'm not sure what they do. There's also video encode and decode. That's very new, the video encoding stuff. And on Intel integrated graphics, there is 1 queue, and you will be happy with it. Just 1. Mobile cards have different layouts. If we go to Android and go to some Samsung phone, we can see that it has 1 queue, but it has 3 queues in that 1 queue, and it doesn't support transfer, which is weird, but I think there is some guarantee in the 1 queue family, and it has 3 queues in that queue family. Yes, I correct myself there. What was I going to say? I forgot. Okay, well, I think that's enough for this week. We've got an hour's worth of stuff, and we can talk about it more after we stop the recording. But thank you for being here with us today.